Hello guys, it's been a while. Haven't worked on the robots for almost like a week. It's Friday tonight, um, so there's a ton of work to be done. So let's get to it. Um, so as a quick update of where we're at and what needs to happen next. Actually, let me get this up the screen. So on the last video, last time we were recording, we got the robot, the first leg assembled, as you can see here, and it's moving. Now it's not moving. It's not moving super smoothly. It's a little jerky, and so there's room for improvement there. But it's good enough. It's moving, and so I would say the next things we should. Oh, so that's that. And I also received a total of 12 servos. So now we have enough servos to actually build the entire dog. So kind of like the next steps would be like in no particular order. The next steps would be to improve the leg design. So there's a few joints that are a little loose that I want to tie it in. So that's important. And so that's like improve joints in general. There's also some parts that need to be redesigned to remove support. Redesign some parts to remove support. There's also some parts that we need to consolidate. So we did remove all the bearings, but so I did this in a quick and dirty way. So I didn't have to reprint the entire thing. So I just kind of like added more parts. We need to consolidate those parts to the existing parts to reduce the number of parts. So I'm gonna say consolidate bearing removal parts. So this is kind of like, this is our to-do for the weekend. So it's Friday tonight. I'm planning to work on these tonight for a couple hours, then tomorrow, and then Sunday. And by the end of this weekend, I intend to have the full dog. Unless something catastrophic happens. So there's on the leg side of things, there is that, and then there's like design the rest of the body. So a couple of things here. First of all, we never designed the shoulder, right? So I'm just gonna unclamp the leg here to show you. But I mean, it's exactly what's on the video. But I'm just gonna put it in the frame here, right? So we have the leg with two actuations here, but we never designed the last actuator here, the shoulder that will allow us to move like that. Imagine like a dog lifting its leg to pee on something. So we're gonna add that. So I'm gonna say shoulder joint. And then when we're adding the shoulder joint, obviously the shoulder joint connects the leg to the body, so we also have to design the body. Now when we're designing the body, the body should be just one part, really, almost like a car chassis or frame. So when we're doing that, we're actually gonna be thinking of all the legs. So we gotta do all legs, 4 legs. Design, mirror the leg. So all the legs on the right side will look like these. So we can just print 2 of these. But then on the left side, we need to mirror some parts, which should be no issue. So we need to do that. But I do think on the body side of things, we do need to put some brain cycles to make sure everything's gonna fit, everything, the battery, everything that we need to fit in the future. Or we can just do a very simple body and as a quick kind of like hacky prototype just to get it together, and then we'll probably clean it up later on. So that's what needs to happen. What else? I wanted to track spending just to see how much I've spent on these projects so far, but then improve smoothen servo motions. So if we see this video here, you see it's a bit jerky, and I uploaded this video, and the reason why I uploaded this video, even though it's like it's only a 30-second video, is so I can share it on Reddit. I also created a GitHub repo here so anyone can see the code I was running. Very simple code. So I uploaded this on Reddit. People gave me some opinions on how to improve. And it basically comes down to 3 things that are potentially causing the jerkiness. So So it's people are like, you're doing three things wrong. Um, um, so first one is power. So these servos are heavy grade servos, and so we don't know a lot about them, but we do know that they probably take more current than we're providing right now. So even though I have an Arduino Uno and it's connected to a 12V source from my power outlet, actually each 5V pin on the Uno only puts out 400 milliamps. And these servos, although they're not rated, so I need to rate them, but I don't have any way to measure current. So I'll do that tomorrow. I'll go to an actual hardware incubator and see if I can measure it there. But even though we don't know how much current they need, we kind of do know that 400 milliamps is not enough. And the reason why we know this is because if you look where these servos are used, so these servos are used for RC cars for steering. They usually allow, you can see from their power sources that they usually allow up to 5 amps. So 5 amps might be their stall current. So basically when the servo is trying to move, but it's locked in place, the motor's trying to push, that's the condition where where it's gonna draw the highest continuous current. So we should be rating towards that. Arduino cannot support more than 400 milliamps, and so we're probably flipping the current overload, whatever hardware it is on the Arduino, and that's why sometimes when I'm running the light continuously, it crashes. So that's one reason that Reddit came up with, and which we can fix. But to fix that, we basically need to use a servo driver, which is a different board, to basically provide parallel power outside of the Arduino to the servos. The other reason why Reddit told me that our setup sucks is the microcontroller. UC, that U should be like the mu, the Greek symbol. So UC microcontroller. So Reddit doesn't really, and this was the robotics subreddit. So these guys really don't like, these guys are hardcore. They don't really like the Arduinos. They were like, you should switch to an ESP32. So there was like this other board, ESP32 DevKit1. So we'll likely have to switch to this board, which they're saying like the clock speeds are better and so on. If we do switch to this board, though, that one of the issues is that these pins only put 3.3 volts on the digital pins, so for the PWM of the servos, but our servos require 5 volt PWM. So we would need to work around that. So there's some stuff around implementing a better controller and providing enough power to the servos that needs to be figured out. So that's gonna be tomorrow, not tonight. And then the other thing that they said we could do better is basically better software, and that has to do with the way we command. Our PWM, our signals are choppy. Basically, the way we're commanding it, it's like, I think right now I'm doing like 1 degree of resolution. So every 1 degree we do like a step change to the PWM, and so that's like causing some jerkiness apparently. Now if I was to rank the reasons, I think software is the biggest gain. I think the microcontroller thing, it's kind of like, it's just kind of like people being picky and not liking Arduinos, but we're gonna do it anyways, just to build a very reliable platform. I use Arduino because that's what I had. And then the power is actually a really good point. We definitely want to have good power supply. I will say that, it's like, software, if I had to rank, like, software engineers are very picky. They're like, oh no, you shouldn't do that. You should use proper frameworks and so on. And so they're very picky about like how you do things in software. Electrical engineers are a little bit like that. So you're like, oh no, you're not using the right microcontroller, your clock speed is not good enough. It's only 16 megahertz. If you switch to ESP32, you can do up to 240 megahertz. I think even if Arduino Uno is only doing 16 megahertz, that's more than enough. If you think about like from first principles, how fast these servos can actually move, like their rotational speed. compared to like the clock speed on this microprocessor, it should be totally fine. But you know, electrical engineers are a little picky as well. Not as picky as software engineers, but still picky. And then from my experience, you know, mechanical engineers are the least picky. They're like, you know, as long as it works, as long as it doesn't explode, just use hardware from Home Depot. So I don't know I don't know if it's gonna make a huge difference to switch microcontrollers, but I'm still gonna do it because I've never worked with these more serious microcontrollers, and I do wanna, you know, kind of learn that. And you know, it's just a very bulky package anyway, so there's room for improvement there. And so I think this is what we need to accomplish this weekend. Yeah. And if you want to see the code and all that stuff, I mean, I'll put the GitHub repo on this video description, on the video description of this video. Yeah. You know, going forward, I'll just start uploading things so everyone can see it, maybe contribute. It kind of looks like this right now. It's very, very simple. Hello world, troubleshooting. There's some videos, there's some code, so you can see it. So that's where we are at. Let's log into Onshape. So I think tonight we can start with the shoulder joint, and then we can do some joint improvement. Yeah, maybe we can do like design and shoulder joint. Shoulder joint is the most interesting part, so I wanna do that next. What else? Also, I mean, before we start, I do want to say that well, first of all, I want to thank everyone who's been watching these videos. So the first video got 2.7k views so far. The last one got 1.2k views. I suspect it's also because it's an hour longer, so 3 hours. So I think we're pushing it really, really far in terms of, like, you know, it's basically like watching a movie, right? So maybe I'm gonna break down our to-do list here into 3 separate shorter videos, just so it's easier to follow along. But overall, I'm just very thankful for everyone who's been, you know, leaving kind comments and you know, showing support. It's very encouraging, and I didn't know if people were gonna want to watch these, and now I feel much better about it. And yeah, I might actually improve the video titles, and you know, from my Reddit post here, I actually had a post that had a pretty nice number of upvotes here, 400 upvotes. It seems like these, like, I'm building my own robot dog. That's the title of that I should be using that on the YouTube videos. But anyways, that really doesn't matter, you know. We're gonna build this robot even if no one watches it, because, you know, we just want to build a cool robot. But I thought I would share that, and yeah, just you know, leave comments. I'll read every comment. I'll reply to every comment. If anyone's building something too, like, I would love to see it. I also posted on Reddit and on Twitter. Sorry, I still call it Twitter. I've been posting some robotic stuff. I posted about a previous robot that I built, and that also got some nice comments. I got some nice DMs. This was the previous robot that I built. It was a food delivery robot. It's much bigger robot. So yeah, and so, you know, I got some DMs. Some people are building other robots, and I always love to see it. Tomorrow, I'm actually gonna go to San Francisco to, you know, meet with someone who replied in person. It's great. It's a lot of people are building cool things, and that's awesome. And we should try to foster this community of builders. But with that in mind, let's just get to work. So this is where we're at. So I think everyone's very familiar with it by now. One more thing on YouTube. I would love to have music, but I think if I put music on these videos, I'm gonna get copyrighted. So if anyone has any workarounds for that, let me know. But yeah, so this is what we have right now. I want to get started with this servo, mounting this servo, the shoulder joint servo. So let's figure out what this mounts to, so some sort of body. And after that's done, we'll clean this design up. But I think it'll be good to start printing the shoulder joint. So we're gonna start here. We're gonna start here, 1, and then probably some sort of 2 here, and we'll do 3, 4 and 5. And really, if we get up to 5 tonight, I'm not sure if we'll get up to 5, but if we do, we can print overnight, and tomorrow we can start assembling all the legs. Yeah. Yeah, that's basically it. Yeah, and I don't know, maybe tomorrow we'll get more comments on how to improve the dynamics, but yeah, just really watch this video. You see, you can see it kind of like jerking. It's like, it's not smooth. At some point, I also have to figure out how to, because right now it's just sweeping the entire range of motion that the leg has, but that's not what we need to walk, right? To walk, we need some sort of walking motion. I still haven't figured that part, and so that'll be fun, but that's something for the future. So I'm gonna close these now, and yeah, let's get to work here. So it's just gonna be mostly a CADing video, 3D CAD, so mostly on Onshape. Now, someone did ask if there's any resources to learn Onshape. So I don't have any resources to learn Onshape. I'm figuring it out as I go. I've mentioned many times that I'm not used to Onshape, and I don't particularly like Onshape, but we can figure it out together. Yeah, and so for the body, I did do some hand sketching. I was sketching some stuff through the week. It's actually nothing amazing, but just putting some thought on it. Obviously, it's not hard to figure out a part with 4 holes to screw down a servo. That's easy. It's more of screw this servo, and then the servo right in front here, so there's another servo gonna go here, you can imagine. And we want to make sure it's a tight package. I always want to make a very tight package, the smallest robot dog we can make. But at the same time, I want to make it easy to assemble, right? So I don't want any screws that are super hard to reach and stuff like that. So that's kind of where I've been putting more thought towards. I think on the last video, I was complaining a lot about how hard putting those bearings into the leg were, and that's eventually why I removed the bearings, because it was just too hard to assemble. I need things that are easy to assemble so that anyone can assemble them, and maybe one day we can have a ton of robot dogs, right? So if you want a design that scales, it has to be easy to assemble. It has to have as few parts as possible. It has to have as few assembly steps as possible, and those assembly steps needs to be very easy so anyone can do them. So that's kind of what's going to be driving this joint design. Now I'm still building on the Dingus, the open source design, right? So this entire orange part I haven't changed yet. There's a few things I do want to change. For example, this opening here actually does nothing for us. I don't know why there's an opening here. Some people might argue it's for thermals, so the servos don't get too hot. That's obviously not the top concern here. But what I'll tell you is these openings actually add a lot of support, because this orange part prints like this. So this bridge in here ends up being a huge overhang that requires support. And so if we were to remove this pocket, just by removing that pocket, we'll remove a lot of support, and our print, might use less material, will be faster, and the post-processing of the print will be much easier to handle. So this is called right leg assembly. I think we need a assembly on top of that includes one of these assemblies. So I think this servo actually shouldn't be here, and so we need to create a new assembly. I actually don't know how to do that, so we're gonna figure that out. Just gonna go ahead and create a new assembly. I'm gonna call these the body assembly. And tonight I'm not gonna, I'm gonna be a little lazy, and I'm not going to keep track of the BOM on the spreadsheet. We'll come back to that. But we're gonna name these Antarctic body. And once we have that assembly, we can actually search the tools. So I actually don't know where to click anywhere on Onshape. I just search tools and search for what I want. So insert, that actually works great. So I should be able to insert assemblies, and yeah, there you go. So I can insert a right leg assembly, and there's the right leg assembly right there. And of course we need 2 legs. So now I'm gonna go and insert another one. And now we have 2 legs. And now we have 2 legs. And of course, I need 2 legs to know how much space we have in between to package those 2 servos. So these servos should actually be on the body level sub-assembly and not the not the leg level sub-assembly. So let me change that real quick. I'm just gonna kind of like narrate what I'm doing, hopefully, so everyone can agree. Now, one of the things I haven't figured out on Onshape yet is how to constrain things, because on SolidWorks, even when you're adding assemblies or parts to a new assembly, you have the origin and you have the planes of the previous part or assembly, and so you can use those to basically keep the same origin on all your sub-assemblies, and so you can just insert new sub-assemblies and make them based on the origin, and so everything fits. But on Onshape, there's no, obviously there's an origin here, but this origin is for the entire assembly, not for the sub-assembly. And so this sub-assembly actually has no origin, so I don't know how to constrain it. And I imagine this is kind of like floating. It's not floating actually. I can move it, but I don't know why I can't move it. Let's see, let's try this. Okay, nothing moves right now. It would be nice if this, whoa. Okay. All right, so I'm gonna do a mate here. Planar mate from here to here. Man, I can feel I'm a little rusty on explaining things just from a week of not sharing my screen. Okay, 2 legs. Yeah, I think we can use the orange part to kind of like constrain things here. And of course, if we eventually do change the orange part, this might come back to bite us, just because if the geometry on that one part changes, then the mates might change as well. Another thing I'm going to go here and do is I'm going to suppress this sketch because we don't need it anymore. That was for the whole kinematics thing that I failed epically at. Yeah. And so yeah, my origin here is very dirty. It's just some random spot here. I guess we can do another mate between here. We can do like a planar mate between here and here, and we can do an offset. I'm just gonna kind of like eyeball it for now. So 200. Okay, so that completely broke. So I'm gonna refresh to like reload all the parts here. And I might be running out of RAM or something. The computer feels very okay. And the other thing I'm gonna do is actually I don't know why it's rendering like that. Oh, refresh. All right, it's not doing what I want, but we're gonna make it work. Sure. Again, on SolidWorks, there's a way you can do it. So like in a top assembly, the sub assemblies do not move, but this is not the case right now. So there should be a way. I need the legs to not be in such a crazy position. All right. Let me just make sure. Oh, okay. Well, it looks like our sub-assembly is not fully constrained. So maybe I can define these as a positions here somewhere. Name positions. Chilling. Oh. Wait, what? Oh. And so maybe. Yeah, and so now I have a position called chilling, and so in my top assembly I can define the sub-assemblies to be locked in position chilling. So this is what it looks when both legs are just chilling, and you can see they're in roughly the same position. And so going back to our offset made here, we can edit this, and you can tell 200 millimeters is not enough. It actually looks like this might be more like a 500. And I'm sure, 500 is too much. I'm sure there's a way to optimize these, but for now I'm just gonna eye it out. Just go with the vibes. And of course, you know, there's some considerations here. We want to make sure the legs are never clashing. But just as a feel, this looks good to me. Right? Like if you imagine proportionally wise, this looks correct. Maybe even too far apart. Like I said, I really want a tight package. Anyways, the next step would be to add some servos here. So let's insert some servos. Let's see if we have the servos here. Part Studio, part 1. No. Can I copy and paste it? Wouldn't that be kind of... Oh, I can. All right, so we have 2 servos here. And if at any point you think, oh, this guy is such a noob, there's some better way of doing that, please comment below and I'll consider it. Yeah, now I think we should package these like this, just so the robot is yeah, because you see that the servo horn is not in the center, it's actually slanted towards one end. And so if we put them this way, then the robot, once this is locked to the here, then the robot goes downwards instead of upwards, and which I think makes more sense to me because you know, lower CG, cleaner package. So I'm gonna rotate these like these. And of course, I'm eyeing a lot of these things out just because this is the first pass, and I just want to move fast, right? So if I'm making a huge mistake here somewhere, we can always go back and fix it. But I'm trying to get to a working shoulder joint that I can actually see in person. Just because I feel like once you have it printed, that's how you can learn the fastest. So yeah, so it's, you know, it's a question of how much space do we need. Obviously there's gotta be a part that connects these this pinion looking thing to here. And it's a question of, okay, how much space does that part need? Obviously, probably not as much as we have there. So let's do another planar mate from this surface here to this surface here with an offset of, I feel like I can fit anything in 20 millimeters. Okay, so that's the wrong 20, yeah, measuring on the wrong. So it's minus 20 actually. Yeah, 20 is too much, right? So we can probably fit anything in 1 millimeter. Is that gonna be enough material? What do you guys think? Let's see. So basically, we're gonna need a screw that connects whatever parts goes in there to here, and then these bolts here will thread to that part. You know, 10 millimeters looks fine to me. Everything's gonna make a lot more sense in a little bit. I kind of like, you know, if I'm not making a lot of sense, it's because kind of like I kind of like know in my head what these should look like. So as I build it and put it together, it's gonna make a lot more sense to you guys. So 10. And 10. The other thing is that tomorrow I'm doing a bunch of things. Actually, I'm going to Y Combinator demo day. I'm test driving some Porsche 981s, and I'm gonna go see that robot from that guy on Twitter. I don't know, maybe I'll bring the camera along. This is not a blog. This is supposed to be we're building a robot kind of like video, but it feels like the content is relevant. All right, so I think this is roughly what the servo spacing should look like. Maybe we're gonna add some more positions. So we have this position here named chilling, which is just random. But then we should have something like here, which is like, this is basically all the way up. All the way up, and then we should have one called all the way down. And all the way down is when this part touches here. All the way down. Whoa. And so this will allow us to just quickly and quick and dirty just see if there's any interference. So if we lock position to all the way up, okay, that's complete. That I feel like that's wrong. All the way down. Okay, that didn't save properly. Chilling. Okay, let's see. All the way down. I don't know how to. Yeah, okay. Did that update all the way up? No, all the way up is still wrong. So I think I can delete these. I obviously can't. Oh, I can update them. Okay, cool. All the way up. Okay, cool. So now we can go here, and all the way up will kind of look like that for the main one. And the rear, it's the front leg that could cause interference issues. The rear one, I'm not too worried about. But if both are all the way up, it would kind of look like that. And yeah, there should be no interference here whatsoever. The other thing to keep in mind is the shoulder joints, right? Because those are, you know, the shoulder joints. You can see that depending on how much we want this leg to rotate, it could, you know, when it rotates inwards, you could see this leg could hit this servo. But I don't know how much trouble we need there. So tonight we're gonna figure that out. But for now, let's just go back to our chilling position, which is just somewhere in between. All right, cool. And so the next step is to create a part called body where these servos connect, and that's where I start to be a little more clueless as to how to actually build this part, but let's give that a try. So I'm gonna start a new part. Actually, let's take some measurements here. Let's measure from here, and I already forgot the hotkey for measuring, but from here to there it's 300 millimeters. So our body will be roughly 300 millimeters. And so let's create a new part, and we're gonna call this part body, chassis, body, rib cage, like a dog. Torso is the word I'm looking for here. And so the torso, From the top, top is obviously a square, and we measured D for distance. Yeah, we measured 300 millimeters, and just to give it a an aspect ratio. Obviously, we don't want this to be a square, so it's gonna be 300 millimeters. But 200 millimeters should be an acceptable, reasonable amount. And then we're just gonna extrude this real quick. That looks too thick. Maybe like a 5 or 5. Yeah, 5. It's like 5 is like just under a quarter inch. And then the other thing is we want to make it clear which one is the front and which one is the back. And so I'm just gonna add some features here that make it clear which one's the front and the back. No, you kind of like, you don't really need these because you should be able to tell from using the proper planes. But like I said, I haven't mastered planes yet on Onshape. And so I'm gonna bring in the body here, and that's when we can start to putting these things together. So torso, sorry, I'm gonna stop saying body, it's torso. So now we have our dog's torso there. And now we can kind of start imagining where things are gonna fit. Something like that. Now, I don't know if we want these all the way up front, right? Because, or maybe we do. We can. Okay, let's just go with all the way up front. Yeah. So let's make these things actually. So now we start to fully define our dog here. Yeah. And then now it's more of a question of, okay, how do the obviously this surface shouldn't touch this surface. We actually need a cutout to clear the entire orange parts. But this starts to look kind of like it. I do think the torso is too wide right now, the aspect ratio. When it comes to design and making something that looks nimble and agile, kind of like a race car, proportions are everything. So the aspect ratio for torso, our dog is too thick right now. The dog is too thick. So we're gonna go, I'm just eyeing out proportions. And again, this is not always how designs go, right? You should be thinking about, do you have enough room to package things and so on. Right now, I'm gonna focus on making a dog that looks good. And after that, I'm gonna make sure, I'm gonna make some magic so we can fit all our electronics in here. But just eyeing things out here right now, getting a feel for it. That looks about right to me. In terms of printing our torso, having a nice flat surface at the bottom would be very nice, would make printing very easy. So I would like to have that. And so maybe another constraint is for the servos to be up here. And so our torso would be like that. Of course, the lower the torso, it makes our legs look shorter. And short legs are not, if you look at a cheetah running, cheetahs have good proportions, very slim bodies. But cheetahs also have long legs, right? They have long legs. Who has short legs? Donkey. Donkey has short legs from Shrek. Think of Donkey from Shrek. Yeah, this guy has short legs. We don't want Donkey, we want cheetah. Cheetah running, cheetah. Donkey is bad. We want cheetah. See, that's the sports car right there. That's the dog I want, even though this is a cat. But so maybe I'll make some exceptions. Let me just see. Let's play with some positioning here. Fully extended, all the way down. Okay. Yeah, that shouldn't be that too bad. I think that should work. Yeah. I'm gonna take a bathroom break. I'll be BRB. 1 second. All right, we're back. Am I rushing? Do you feel like I'm rushing? No, we're not rushing. You're rushing. If we have the torso meet the servos in this surface here, see that screw is gonna be hard to reach, right? Unless we have a big open cutout. Also, this orange part cannot actually meet the torso here at the front, just because. Oh, actually, also we said this is the back, but so this is. I guess that's the front now. Cannot meet it here at these surfaces cannot be at the very front, just because we need a pivot point here. We need some sort of shaft going in there. So we're gonna have to add more material, but yeah, let's do that right now. Torso. And like I said, I think I can fit anything in 10 millimeters. That's enough room to fit anything in this world. So I'm gonna do it like that, and I'm gonna change our mates. Our mates here. I wanna add an offset. Offsets are your friend. -10. See, like SolidWorks has a button here, so you don't have to do -10. You can just click a button and change the direction. But I don't think Onshape has that. Sorry, SolidWorks has a button to change direction. I don't think Onshape has that. All right, so something like that. Yeah, something like that. Now, these servos here should be all the way out. Because why wouldn't they? I mean, maybe we want a wall to protect the internals, but yeah, I don't see why they wouldn't be at the very outmost. So let me just take a guess here and do another 10 millimeter offset. Again, 10 millimeters, you can fit anything. Whoa, no, okay, 10. Yeah, starts to take some shape. So something like that, I think. 10 might be too much. But yeah, something like that. Again, I'm just doing quick and dirty work here. And so the next step would be to figure out the structure for the servos. You know, the other thing that comes to mind is, why are the servos vertical? Why not put them horizontal? Because if we put them horizontal, that will actually, well, let's try that. I think if we put them horizontal, we'll actually gain a lot of options. Okay, so that's good. What is this? This is good. That's good. Cylindricals are good. What's actually constraining these? Oh, I see. I already forgot what mates I have where. That's what happens. Planars. Oh, I see. Let me get rid of this one 1 second, and this one's good. That one we can keep. This one we can keep. We can keep. Okay, so now we should be able to rotate this guy inwards like that. 90 degrees. 90 degrees. 90 degrees. And the only issue I see here right now is obviously the wires are going outwards of the dog, which is not great, but I think we can make this work. And I think it's going to give us a tighter package. Again, just kind of like imagining things in my, oh, actually rotated the wrong way. The wrong direction. Yeah, so if we go this way, and then the torso can come all the way up. And our legs are gonna look longer, which is good for proportions. And yeah, of course we have collisions here going through the orange parts, but that's fine because we need cutouts anyways. And I think that's fine. Yeah, so let's try doing that. Let's try doing it that way. And I also think it will be much easier to mount the servos this way. All right. So if we're doing that, then I'm comfortable with saying that this surface and the servos are gonna touch. And I think, oh, and then we need to define this one here. And like I said, going back to our completely made up 10 millimeter offset rule here, we can fit anything in 10 millimeters. See, there's a flip primary axis, but it's the wrong flip. That's not the part that I want to flip. Okay, so something like that. Does that make sense? I mean, I think the servos are taking so much room in the body, and I think if we were to add servos on the other side, it would actually be very tight. If you start to think, you know, oh, so these, oh, sorry, these face, and I don't like doing mates to the faces, but I don't have any planes here to lock to. Can I lock it to the? Yeah, see, I cannot. I guess this is technically not a plane. I want to make it parallel to the right plane, but it doesn't doesn't matter because like it's relatively parts, the relative position between parts seems fine. Now 10 here, it's probably a stretch. We can probably get away with 5 millimeters is a lot of millimeters, and so that will give us a tighter package, which probably doesn't really matter, but I'm obsessed with, you know, tighter packages. Feels like, again, going back to remember the cheetah. We want to be cheetah, we don't want to be donkey, right? So donkey, it's like not a tight package. Cheetah, very tight package. We want to be cheetah. Yeah, something like that. I do think the legs could come slightly together, closer together, but we do want to have some room in the body to actually fit. You know, we gotta fit a battery, we gotta fit the microcontroller, the power supply board, probably more things that I'm not even thinking about, like a Jetson somewhere, you know. It's like, yeah. So something like that. I do think we might need to extend the torso a little more, because this is not going to be enough room to add a beefy, or it might be, add a beefy pivot point for our shoulder joint. Let's see. So I'm going to give it 340. 340 is not bad. But since I added some material there, we do need to add it back here. So now it's not -10, it's actually 20. Right? So that gives us much more room to add something beefy there. Cool. Now in terms of clearance, we need some pockets to clear these guys. And I think that should be super easy to do. So if we could just edit this part here, and I think on shape that makes this easy. Edit in context, yes, and then we can add a sketch here, and then we can, oh, wrong kind of square, cornered rectangle, sorry, not a square. We can do something like that, a pocket there, a pocket here, line, construction line, construction, and make these a horizontal or vertical line in this case, I guess. vertical, vertical, nice. Okay, and we need some dimensions. And can we oh, okay. Sorry, I keep pressing M for measure, but it's actually D for distance. I guess we could make our cutouts to the actual part on the assembly, but I think that's a bad practice because, you know, what if the part change and stuff like that? So let's just do not reference any other parts on our part sketch. So let's go with 50 here. And looks like, again, just kind of like eyeing things out here, you know, 15. For moving parts, I think, you know, it doesn't hurt to actually have a lot of clearance, but 10 is too much. Oh, we're gonna have to go with fractions. Okay, how much is this? Oh, it's not even straight. Okay, well, let's start here, see how things look. It doesn't have to be symmetrical, of course. A symmetrical design is always nature's way of doing things. So let me go on the part now that we have this sketch on in the torso. We can use this sketch to carve out the pockets, carve out the yeah, just like that. And that should be roughly, I mean, that might be a little tight, that gap there, and a little too wide up front. Yeah. Yeah, so we have, let's actually measure, because, okay, so we have 1.5 here on this side, and we have 7.5 here, right? So 1.5 plus 7.5 equals 9, so it should be 4.5 on each. So 4.5, so we gotta remove 3 from one and add it to the other. Easy math. Remove 3, 12.5 minus 3, and then 17.5 plus 3. And we end up with some funky numbers, but in the name of symmetry, I'm gonna call this good. Again, moving very quickly here, just trying to get to something that looks just about right. Did I do that completely wrong? Like completely wrong? Yes, you did that completely wrong. Okay, what one? Oh, I see. 1.5, okay. I added it twice. This is the thing with doing things live. Every time you make a mistake, you look very you look very dumb because to the people watching, because they're like, oh yeah, they, you know, they're not doing this live, so they're like, you guys can probably think things through and be like, oh, why are you doing things wrong? That's basic math. You should get it right. And I agree, I should get it right. Oh no, wrong part. .5. That looks, I mean, I'm comfortable with that. All right. So that's kind of like the cutouts now. Obviously, I went deeper here to account for the shoulders moving. But I don't know if that's deep enough or not. We're gonna build the shoulder joint and then figure out how much can these like actually move that way. So let's do that now, I think. So some of these original mates we used to like put things together now can be removed because now we have a torso holding things together. So that this one can go, so the legs can rotate freely. This one can go. This one can go. Yeah. And then really everything that's constraining the legs are the servo positioning. So this servo positioning needs to be locked in place. And so we're gonna do another sketch in context here. So ideally, we can edit this part in context, in a context that's like that, parallel to the surface. And so what we're thinking about here is we need to add some walls here that just touch the servo in the mounting points. So somewhere like that, and yeah, somewhere like that. And I did say I wasn't gonna use any other external parts to make our drawing, and I'm gonna try to stick to that promise because it is good convention. That just ensures that things are not breaking apart later on. So that one's a construction. So what we care about is this distance here, this distance here, and then this distance here, and then this distance here. And of course these numbers are completely made up. Just give me 1 second here. I'm gonna figure it out. So 13.35. And again, there has to be a cleaner way of doing this. It's just I am kind of like not super well versed on shapes. So I'm kind of like just doing this quick and dirty. Here to here, 12.25. A lot of 0.25s. 12.25, and that's the beauty of using a 3D printer. Really, you can just kind of like, you don't have to worry too much about having like ugly numbers like 2 decimal points, because the printer doesn't care. It's not like you're machining these. It's not like a human has to figure out how to properly machine these things. So you can really get away with some ugly numbers. Okay, let's not cross the middle plane. Yeah. So now that we have that here, we can extrude these as a thin, I think, as a thin, yeah, thin, here and here on the other side. And how tall? No clue. Something like that, right? And so, just again, quick and dirty, everything's quick and dirty. And so now that's where our servo would mount, right? Makes sense. And it's really hugging it tightly, so we probably want to add some clearance here on the sidewalls here, like here to the servo. But just for now, let's keep it moving here, guys. So the servo is constrained by touching these, but it's not constrained in this axis. It's not constrained in this axis because it doesn't know that it's supposed to be touching that wall. And so let me tell it that it's supposed to be touching that wall. And so it's like, you guys here, you touch here, and you don't move from there. Whoa. You touch here, touch here. Oh. I'm gonna lock the torso in place so things stop shaking. I don't know why this isn't moving. Oh my god. Well, okay. So this is kind of like how the leg's gonna rotate on the shoulder joint. Cool. You can kind of see it working. I don't know why this servo here. Okay, so it seems to think that some mates are clashing. So what is this? Oh, okay. It's because it's a fasten mate. We don't want a fasten mate. We want a planar mate. Yeah, like that. Okay, and we said, apparently I missed one mate here because we said these guys were gonna touch here. Yeah. I hope this is making sense. I don't know if this is entertaining to watch. Hope it's making sense though. All right. So something like that, right? Something like that. Of course, we need to add holes to that wall so the servo actually mounts there. I do think, you know, if we put a screw here, it's going to be a little hard to reach because, you know, eventually there's going to be a wall here on the outside, and I guess you got to fit your Allen key from here, but especially this one down here in this corner, that's going to be tough. But let's just keep it moving for now. And now we can see how the leg rotates, and that will give us an idea of on whether if our cutout is big enough. And obviously, I mean, it sounds like the answer is yes. Obviously the question is how much do we want to allow it to rotate, and what's the hard stop, right? So ideally there's a hard stop there. You know, imagine you lose power. If you lose power and your servos are just like rotating freely, how far can you move these, and what's going to keep it from moving further away? So right now, as it is, your two back legs would actually clash, because you can see the tip of this leg has passed the middle plane, which is somewhere around where this dot is. And so you can have your two legs clash if your robot is off. I don't know, it's not a big deal. And then the other way you really can go all the way. And remember, the main reason for this joint, for the shoulder joint, is to give us some artistic freedom, right? So we want to make this dog walk in an interesting way, and so that's the main reason of these shoulder joints. So, you know, the more, you know, rotation, the more motion we can permit, the more options we have towards like animating the motions. So that's good. So I mean, this is a ton. I don't think we can actually do, well actually, yeah, maybe we should try to do like 90 degrees leg, like just like that. Again, like a dog peeing on something. Maybe that will be one of the key motions, like the dog can pee on things. I mean, now I'm just assuming it's a male dog, which, you know, no one said that, but I mean, would it make sense to allow for something like that? No, right? Or would it? First of all, this already crosses the middle plane, so it will be clashing. So maybe that's what we should do it. Like middle plane is what drives it. So you go up to there somewhere. But the key takeaway here is that our cutouts are good. And up to there somewhere. Yeah, I think I'm happy with these. And so if this looks just about right, we can add holes for the servo. We can build the pivot point here. And then we can print these. And I think that felt pretty fast to me. I don't know, maybe we spin it around a little bit and give it more thought, but I think seems correct. Seems directionally correct. I'm gonna do a sketch here, editing context. I want to add a sketch here, and I think there's a trick here we can do where we take the geometry of the servo, yeah, here, and we use it, and then we save that, and then if we go to the torso part, we have a sketch with that geometry. And what is this? Context. This means context. So we want to break the context. We don't want external context, but if we remove that context, now we have a sketch that's just not defined by anything, kind of just exists. And so we need to define it. So, you know, we know that, okay, we remove all external context, right? So we don't have the context arrow anymore. And let's see what we have here. We have radius. So it's a radius because, why is it a radius? It's because it's not a circle, right? So circles have diameter, half circles have radiuses. So let's do it here, construction line. Let's fix the distance between our two circles. They're gonna be circles, they're not circles right now. I'll make them circles. 4.75. 5. Okay, so the numbers are very clean. You can see that these servos are in millimeters because they're Chinese. If they were American servos, there would be some imperial thing. 2.15. 2.15. Let's just draw new circles, I guess. 2.15 radius. So obviously, if 2.15 is the radius, then the diameter is 2.5 times 2. Not the cleanest number. Let's see. Boom, bam, boom. 2.25. 2.25 times 2. Nice. And so now we have that. And with that, we can remove this material as a solid. Remove, boom. Now I don't like doing depth here. There should be an up to next kind of thing. Direction. Okay, maybe there's not up to next. In SolidWorks there's an up to next. Oh no, it's because it's blind. Up to next. There we go. Okay, so now we have our holes that, if we go back to the assembly, matches exactly our servo, and we don't have external context, so it's great. And the reason why I'm only doing one servo, by the way, is because we can mirror these. These torso is it's bilaterally symmetrically and symmetrically in that other plane, so we can just mirror things and save a ton of time. We could even mirror things like, we can create a new plane here in between these two walls where the servo mounts, and mirror the holes onto the other wall. So at least that's how I would normally do it to save time. So we can do a middle plane here. So that's our middle plane, and then we can mirror these feature. We can do features. Part mirror, no, feature mirror. And you can select these two holes, and then the mirror plane. Select mirror plane, and then there you have it. And then you'll see that if you go back to the body here, these holes line up perfectly. So that's neat. That's cool. So what we have that, we're making progress. And then the next thing I want to do is figure out this pivot here. So on this side here, we're not going to use these 4 holes. We're actually going to use only this internal cutout here. And so we want something that comes from here and then has like a cylindrical feature that goes right in there, right? So, I mean, it's very simple geometry. The thing is, if thinking of like, how we're gonna reprint these, it's like, these will likely require a lot of support. And that's fine. That's fine for now. Again, I like going straight to something I can touch, even though I know it's not perfect, which is exactly the case of this leg. But it's so much easier to improve it once you can see it in person, and you catch so many more things that are wrong, so many more things that can be improved once you actually have a part in your hands, instead of just 3D CAD. And that's one of the beauties of 3D printing. You can get parts in your hand, you can feel it, you can touch it, you can get a sense for the size, for how things interact with each other, without having to wait a ton of time for things to be built or prototype, as you would with machine parts and things like that. All right, let's keep going. So for this guy, this one's actually a little more tricky. I'm just gonna put a mate here. It's gonna be a temporary mate. It's gonna be a what do they call it here? A parallel mate. And it's just temporary, just to get everything lined up perfectly. And then we're gonna do a sketch here. We're gonna edit this part, I think, in context. I think I can never find, okay, edit in context. And we're gonna do our same trick here of using the feature. It's called use. And well, first you start a sketch on the surface, and then we use or project this entire part. And we can also do it with these. Actually, I guess we don't need the entire part. that one we can do without. We're just gonna use, quote unquote, the cylinder here, and because it's a circle, a hole, it's gonna take the widest diameter. Yes, you can kind of tell. So we have that now, and then the other thing we want to know is actually how deep to go. And so we can, I guess, does it matter? Okay, for now, forget about it. Let's just go back to our torso, start building some geometry around here. So of course, you know, we cannot actually build a wall there because it's floating. Oh, actually, yeah. So what we want to do is we're going to add material around here and here. And like, what I'm thinking about as I do these is like, we're building a wall where that's going to hold that cylindrical feature that connects to the shoulder joint, right? So we want to make this wall. This wall is super important. You know, this wall is going to hold the load from the entire body to the leg. So this has to be beefy. And so I'm thinking like, okay, this wall needs to actually be well built. If there's something we don't want to fail, it's exactly this one. So maybe we'll go big. And now I'm going to start by removing this external context. We want this arrow to disappear. So I see we still have some external context. Okay. And now, okay, numbers are not too bad. This is just going to be a construction line. And I'm gonna just keep these for future reference. I don't think we need it anymore. It's not fully defined. Always fully define your sketches, guys. Fully defined means all the dimensions are fully accounted for, and you know a sketch is fully defined when it's black. If a sketch is not fully defined, it will be blue. And this is true for SolidWorks as well. I think for CATIA, if I remember correctly, CATIA, you know, CATIA's, instead of blue, CATIA uses, I think it's like a pink, and fully defining CATIA is blue, which is, I think, kind of confusing, if I remember this correctly. Okay, so now we have these, we can do a thin here, and something like that. Yeah. Of course, how tall, I actually didn't check that, but, you know, let's go back and check here. Obviously, that's more than enough. And then the next thing here, I'm gonna do another sketch. I'm gonna do another sketch, this time for the cylindrical feature that's going in there. What's something to keep in mind? I guess I'm gonna do it this way. It's you know, it's kind of like the quick and dirty way, but edit in context, add a sketch, use, you know, and then you do cylinder. We're kind of repeating the same steps over and over. That's basically what CADing comes down to. I am curious about how deep we want to go. So let me do a section view here. And basically from this face, which is where our sketch is, how deep can we go here? And so the distance is 14 millimeters. Remember that number. I'm going to write this down, 14 millimeters. That's how deep our cylinder shaft has to be. And of course, you know, we do want to give it some slack, right? Cannot be exactly 14 millimeters or else it's too tight, but all right, so here we are. Again, remove the external stuff. Okay, no more external stuff, and then, you know, it's a 5.8 remove 0.2, just to because, you know, it needs to fit. If it's the same size, if your shaft is the same size as your hole, it's gonna be a very tight fit. But if your shaft is much smaller on your hole, it's gonna be a very loose fit, and it's a lot of play, and then you end up with like joints like our knee, which actually, you know, shakes a lot. It's not terrible, but, you know, by a mechanical engineer standards, shakes a lot. Now we could define these to a wall, or we could also define these to the center of this feature, which happens to be just there. Construction, and then make these a vertical. And so now our sketch is fully defined with only 2 dimensions, which is pretty good. So now we have a nice circle, and then we're gonna extrude it, solid, at, and we set 14 millimeters, right? 14, remember that number? Remember when I said remember that number? This is that time. So now we have that, and you'll notice, or you might not notice, but you know, something to keep in mind is like, we need to transfer a load from this cylinder onto the torso. So all the material on top of the cylinder is really not doing anything. So we can remove it, and you know, might as well remove it now. It doesn't hurt to remove it now. And so I'm thinking, you know, it's gonna look something like that. So these lines here will be tangential to this circle, just like that. Tangential. Oh man. Tangential, please. Be tangential. Tangent, yes. And M will cut off the excess. I don't know what M is actually. M for trim makes a lot of sense. Of course, trim could be T, but no, it's M. T is probably something else. T is tangent. Oh, there you go. And then dimension. I'm gonna dimension this as a wall. So, how much thickness do we want past the cylinder to support it? 5. So now we have a fully constrained sketch here, just from those basically 1 dimension, right? Now, to remove, you know, a good practice would be to also include the rest of the face we want to remove here. So let's do that. Fully constrained, perfect. Sketch is done. Extrude, remove, extrude, up to next, and something like that. That looks good, right? And so now we have that. Now there's a lot of best practices we can do here. So for example, first of all, yeah, like if you look at this cross section, section view, our cylinder goes all the way into there. We gave it clearances to the sides, but not on the axial. So we should add clearance on the axial. And then here you have sharp corners. One of the key principles of, you know, proper load transfer is do not have sharp corners. Sharp corners concentrate stress. So you want to give this a nice round fillet or chamfer, or you know. So let's go back in there. So first of all, so this was exactly 14. Actually, let's give it, you know, 13.8. You know, 0.2 clearance. So 13.8, and like I said, let's give it a nice fillet here. As big as you can fit, really. The bigger, the better. Can we fit 5? I don't think we can fit 5. We can probably fit 2.5. Yeah, and then, you know, I'm just gonna like do a little touches here. I'm gonna add a chamfer at the top, just so it's easier to, quote unquote, easier to assemble. The 0.5 chamfers basically do not show on the print, so I'm gonna go with 1, see if that looks better. But okay, section view now. So what do you notice here? So first of all, we have clearance axially and on the sides now. And we have chamfer here, so when, you know, the shaft is going into the hole, kind of like guides it in. And then we have this nice fillet here, very nice stress transfer, load transfer, yeah. So that looks good to me, or that looks better. Of course, it's still a raw design, still half-baked design, but we're getting there. Obviously, the fact that this shaft is transferring the load to here with a nice fillet means nothing if all of this thing is just basically on this cantilever section here, right? So we need to beef that up. Yeah. But yeah, I think it's looking much better. What else should we change before we print this? I guess all the material. Yeah, I definitely want to make this part more stiff. Like not enough material there for sure. So now we're mostly working on the torso. And again, you see here, everything here will get mirrored on this plane and then on this plane. Yeah. Yeah, I'm also concerned about how small this feature is, right? So maybe we'll close it up here. If we do that, we create a huge overhang, which is gonna require support to print. So another way of reinforcing this very small thing is to add a wall here, which is fine by me. I think it just makes manufacturing, it will make assembly harder because like the screw that goes in this hole is hard to reach. But yeah. The other thing is that we really only have one leg assembled right now. So if we just want to print the torso real quick, we can print one section of it. We don't need the full torso right now. Just to like the risk. Even though eventually we might have to, we do have to print the whole thing. And so if we get it right the first time, it's kind of like a waste to not print the entire thing. But you know, are we gonna get it right the first time? I don't know. Yeah. Yeah. Okay. So yeah, let's add a wall here. I'll feel much better. I'll sleep better at night. Let's do something about here. Let's round these corners here just for aesthetic purposes. You know, what I'm thinking is when we mirror these, there's going to be another wall here. So this is going to be a perfect square already. What else? What else can we do? Let's start by adding that wall here on the right here. Yeah, I'm gonna add a wall here. So just from here to here, because we're gonna mirror it. So, and we don't need any dimensions to fully constrain. We'll make it as thick as possible. Thin. It's called, the feature is called thin, but we're gonna make it thick. So as thick as possible. We do need clearance for these holes. I don't know if we can get away with 5. Like on paper we can, but you know, there's a screw head that needs to fit in there from this side, and it might be a socket head, but it's still very tight. It's very, very tight. So that's not gonna be fun to assemble. But structurally, that feels much better. This material here, kind of like by the servo horn, it's kind of like not doing anything, I think. So this could be some extra clearance. Let me just validate. Okay, yeah, this wall. Oh, no, okay. So this wall should go all the way up here. 2.75. So we can do a little trick here called move face. And it's a quick and dirty way of moving this by 2.75. Now it's all the way to the middle, which is good. And yeah, this is the main concern now. The main concern is cleaning that up. We would want to extend this wall more towards this side. Yeah, I think that would be nice. So maybe this wall extends here, eventually meets this wall. Right. And that might also act as the hard stop for the leg. Although I do think we want to enable the oh, I'm peeing on something in motion, and so I'm going to increase the depth of our cutout here, which was this one here. Just for that, I'm peeing on something motion, and I'll make sure that we actually use that motion at some point. And of course, that is actually bad structurally. Because it cantilevers even more. It cantilevers this even more. So we really need to beef that up. But other than that, I think it's a good idea. Okay. Now, before we start beefing things up, let me do some stuff here. I'm rounding it up because I'm thinking of adding a wall that runs through this outside face, and it's much easier to add the radius before building the wall. So I think that's good enough. I mean, I think that looks clean. Yeah, and so remember how we took some time to round these off very nicely? We might have jumped the gun there, so I'm gonna undo that for now. Back to this big square. I'm gonna keep that sketch because I think we're gonna use it later, but basically what I'm thinking is basically something like this. Basically new sketch, and we're gonna use this radius here, this fillet, and we're gonna, oh no, this I'm not done. And then we're gonna add a liney line from here to here, and a liney line from here all the way to here. That should be fully constrained, and then we're gonna extrude it, even though we're gonna extrude it thin other way, extrude everything. Something like that. That's what I had in mind. So I'll give the body much more rigidity. What do you guys think? And I would still want to improve this one here. Extend all this face all the way here, out here. That's not gonna do much though. Yeah, I'm still concerned about these. But see, just so you know, I don't know if everyone can imagine what this is gonna look like once we mirror things, but you know, just so you can see it, you know, we're gonna basically mirror. I wonder. I don't think we can do a part mirror, but it's a very big feature mirror plane. I don't know why it's red. It feels like red is not happy. Okay. I missed some features. Oh, come on. I don't know why that's not. That should work. Yeah, so it's kind of like, oh, I missed one feature here. I missed the extend phase. No, I did not. Okay, obviously there's a gap in there which shouldn't exist, but it's kind of look like that a little bit. Gotta take a bathroom break, BRB. All right, so I can already tell we don't have enough room for the batteries and stuff. A lot of these force of space, for example, the gap between these two walls, it's kind of like useless. You know, it's like 20 millimeter. Like, what are you gonna feed in there? You're not gonna fit a battery in there. You're not gonna fit a microcontroller in there. You're not gonna fit a power board in there. So it's kind of useless. So I'm just gonna keep going for now. Yeah. I think we're almost to the point where we could print something here. Gonna get rid of this mirror for now. I just want to show you guys, just so you can follow along what I was thinking. Yeah. So I think it's looking okay. You know, first pass, not bad. You know, what do you guys think? First pass for first pass. You know, I don't know how long we've been recording. Actually, I don't have a way to tell. Maybe half an hour now. You know, half an hour first pass. It's not bad. I've seen worse. Have you seen worse? Yeah, everyone's seen worse, right? Well, yeah, the point is not to get everything right, just directionally correct, and we're gonna come back and clean up most of it after. So this feels inefficient, but it does make me feel a little better. Not my favorite design there. Again, it'll be great if we can make this functional, not just like mass, not just, you know, structural mass, you know, actually have something there. So we do want to eventually have a tail in this dog, and so I guess the tail will fit somewhere in there. But okay, what else do we need before we're like, okay, we can print this? I think the other thing is, again, these socket heads here. Will the socket head fit? I think so, but should we take the chance? I don't think so. Actually, we'll take the chance for the first print. We'll take the chance. I'm willing to take that risk. Okay, those screws there, screw there. Yeah, I think this is directionally not terrible. Alright, so let's try to mirror things now properly. Let's see what this looks like. New part, remove part mirror, face mirror, feature mirror. So many types of mirrors. Feature. I think that covers it all. Mirror plane. And then you want to reapply features. I don't know what's the difference, but it makes a difference. We obviously missed something here. Oh, we missed a lot of things. I mean, I don't know how I could have possibly missed this wall. It's right there. Why is there no wall there? I clicked on it. I clicked on it. I'll click on it again. Dude, I clicked on it. What? Oh. What about these holes? Why are you ignoring those holes? What the heck? There's another way of doing this, which is basically split, remove, I think remove, split. So we can split part, split with this plane here. Keep tools, no. Trim, no. Face, yeah. Keep both sides, no. Keep this side, yes. Oh. Alright, wrong plane. Yeah. We can do it like these, and then we can mirror the part. Yeah, part mirror. We can add in this mirror plane, and that should be it. And it'll look something like that. And again, not super happy with that space there, but at this point we haven't really fully fleshed out what the electronics look like and what they need in terms of space. We also didn't define a hard stop here, so there like some clash, so we don't have hard stops, but it's kind of like what it would look like. Oh, we also didn't add clearance for the servo, so it's gonna be a very tight fit. We should add clearance, it wouldn't hurt. You can never trust that the servo CAD is exactly precise to size. And then it wouldn't hurt to round these corners everywhere, but you know, that's kind of like 3 points. Alright, so maybe we do that right now. So undo this mirror. Let's do the alt move face trick. Move face and move face, and let's just give it something small, like 0.2, other direction. So we're shaving some material. Perfect. And let's also split this with this, keep this. This is the actual corner that we've designed today. So now we can mirror these 4 times or 2 times. Entities to mirror this part with this plane. Now, my only concern is that this is going to break some mates on the other assembly. But let's try it. Let's mirror these, Boom, boom, boom. So it's kind of like what that full torso looks like right now. It's very small, very slender. Something broke. I don't know what broke. Well, giving a lot of freedom to the legs here, but okay. So it's something like that, and I was hoping, you know, the space in between here, that's where you fit. Yeah, the microcontrollers and stuff. We still need to mirror the legs, and obviously this torso is like a convertible, so it does need to come. We need to put something on top, and maybe that will give us more room. This is just a very basic platform. So yeah, so we set shoulder joint, so this is done. I'm marking this done. Body, I'm marking this done. Improve joints, we haven't touched any of that, so we can start printing these, I think. And it's almost midnight here, so this might be like an overnight print for me, just so I can go get my beauty sleep. I don't know, what else do you guys want to do here? This does feel like a huge clearance gap, which obviously is overkill, but yeah, we don't I don't know if we I guess it's so we can pee on things, right? We'll make sure it's worth it. Yeah, I think I feel good about these. I guess the other thing we need in order to actually use these is a servo horn to connect these to these, so we can do that right now. But other than that, I'm down to start printing. And I'm sure we'll learn lots from the first print. Oh, the other thing is, I don't know if this even fits in the printer. So this is 340 millimeters long, bamboo P1S. I should have checked this before. P1S bed size. Oh, it doesn't fit. Oh, I mean, maybe at an angle? Okay. Let's check that right now. Maybe we have to do a major redesign. Where's the export? Export right there. Export STL torso. So we export, yes. So we open Bamboo Studio. I just got excited. I just totally forgot this has to actually fit in a printer. Creating projects. Torso. No, not even close. I guess we're gonna have to split the torso in half. That's so nice. Well, that's unfortunate. So see, if you have to split the torso, which way would you split it, right? Three, like right in the middle, so you have two parts. Somewhere in here, so you have three parts. But potentially cleaner looking parts. Right in the middle is nice because you want these, the alignment between these and these holes, it's kind of like, it's important. And if we split it like that, it could make assembly easier. So I guess we'll split right in the middle, and then we're gonna have to add some flanges to screw things together. Yeah, I mean that's how you make a 3D printed dock, right? Like, because it doesn't have to be entirely 3D printed. Really, this square here could just be anything: piece of wood, piece of cardboard, piece of plastic from the store. But if we're gonna entirely 3D print it, then yeah. Okay, so for tonight, I want to split it right in the middle and start printing it. And obviously that's fine. Like for now, till I figure out. I just want to erase the joints and like the fits and that in the direction it looks correct. But okay, let's finish this part here. So what this part needs, actually we can build from one of the horn. I have a horn file here. Not this one. This one. Consolidated servo horns. So basically, so I know these servo horns fit perfect. That's why I want to use them to build the next horn. Hydration break. Okay, so we have 4 holes here, need to mate with. Basically, we're gonna screw into these 4 holes. These are 3.2s. Yeah. Servo horn, not this horn. Yeah, so the way, when I printed these and I put these here, these basically fit, I think all, it's hard to tell, but I think they went all the way in basically. And so maybe I can copy this part? I can pattern it, linear pattern, yeah. Linear pattern apart, yeah. Linear pattern new part in this direction, and this distance really doesn't matter. Oh, doesn't matter. Okay, there, and then we can delete some faces, and we're just gonna build up from these, which I already know. Delete face. I already know this part works well. I know it prints well. Yeah, so we can start from there. I'm gonna call these, this is a shoulder horn. And so when you name the parts here inside the parts studio, you can go into your assembly and you can just insert it by the name. So if you go here, consolidated servo horn, drop down, shoulder horn, and it's right there. And it actually look, I hate it, makes it disappear every time. Actually looks quite beefy here. I'm gonna hard stop this in half an hour. So that's, we have half an hour to figure this out. Which it won't take half an hour. No, it's pretty quick. Okay. Wait, okay, small thing, but I just want to change the color, please. Everything being the same color is so boring. What color do you guys like? We've been doing we've been doing blues today. Last time we did greens. Today's blue. Okay. So these and these mate. Planar. No, planar here. Always chooses the wrong faces. It's kind of annoying. Planar. something like that. Oh, we have interference here. Good thing we are checking. So actually now this gap feels too big. Oh, actually it's kind of tricky. Okay, so we have 2.5 millimeters to grow. Oh, wrong part. So we can move our face here. 2.5. Right, something like that. Yep. Now we don't need to move everything 2.5, so I don't want to move these 2.5 because whatever it was before works great already. And the screw that I have, the screws, I bought a bunch of screws. So the screws I have work great for what it was before. Like the length was great, so that will stay 2.5. There's some interference here that we need to clear. 13.5. So here we're going to come down a little bit because I need to create, I need to clear that interference, and I need to create some clearance for some, I guess, wait, what, how would this assemble? I guess, oh, they screw from here. I don't have to create clearance. I just need to make holes. I guess we do need to clear these here, but we can fix that from the torso side of things. Okay, let me do something quick and dirty again. So I'm gonna edit this part here within context. Wherever that option is, I don't see it. I never see it. Edit in context. I want to start a sketch on this face. And then I'm gonna use, where is use? I wanna use, where is, oh, use the entire face here. Like, what I care about are the holes. This hole, that hole, this hole, and this hole. That's what I actually care about. Okay, good. And then I'm gonna go back to the part, and I'm gonna edit the sketch. I don't care about these. Don't care. Do not care. Please go away. Go away. Go away. Go away. All right. Perfect. Perfecto. Okay. So this diameter 3.2. So that's an M3 right there. We can tell it's M3s. So instead of dimensioning all of them, we should be able to tell on shape that these are all the same. Equals, created equal. And then there's a bunch of ways to dimension a circle pattern. You can do a circle, you can do angles, you can do lines. I'm gonna do lines because why not? Lines, 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 lines. So these should be vertical lines. So these should be horizontal lines. Yep. And there should be construction, 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 construction. And then you need dimensions, 9.9, interesting. 9.9, still very interesting. I'm just gonna do, oh no, that's terrible. There's no center, there's no, okay, another line. I should be able to do concentric from this point. Yep, there we go. Another line. Okay, well, I mean, this was obviously the most complicated way of doing these, apparently. Almost done here, guys. Almost done. Okay. Why is this not fully defined? Of course. It's because this is not centered. It has to be centered, the midpoint, and now everything's fully defined. We can extrude these, and then this, and this, and this. Remove up to next, and it'll look something like that. And then if we go here, and then we do like a cross section, a section view, something like that. And then the screw will come from this side. The screw will go from that side though? How? How is that gonna... How does that work? Okay. Well, the screw will come from that side. I'll just have to disassemble the existing one. Yeah, that makes sense to me, right? Right? Or am I just convincing myself that that makes sense to me? Now we might have some clearance issues, but this part is too chunky anyways. There's too much thread engagement. We don't need that much. So I'm going to reduce it by 3.54 by 4. So I'm gonna go here, and I'm gonna reduce this part by 4, and hopefully what I'm doing here kind of makes sense. There was a bunch of ways of dealing with this interference bit, but this is one of them. I think it's fine. Something like that. And yeah, I know it looks funky. But something like that should be fine, I think. Yeah. I mean, not my favorite part ever. But it should be fine. Yeah, I don't like it because like these will require support. That's what I don't like. But it should be fine. And there's no clearance issue. Yeah, I think that's fine. Now going back to the torso, we're gonna split it, and this is gonna break. This is gonna break some. I'm gonna do something dirty here just for printing purposes. And I know I keep saying I'm doing dirty things. Okay. One day we'll come back and we'll do it the right way. Oh no, it's not gonna happen, but we're gonna say we will be. We'll make a promise, a pinky promise. I'm gonna split these. Just as a reminder, we're doing this because like it didn't fit in the printer at first, so desperate times equals desperate measures, and so something like that. I'm gonna close these just because just to give my print a little more sturdiness. This is not what the final design is going to be on this chassis. This is not how we're going to actually split the chassis, but for now. Yeah. Okay. So that should be good. So today we've ticked we've done 2 things. And so I guess I'll print these. I'll assemble it, and that will be the end of one video. So this video is not like 2-3 hours long. It'll be just like an hour long, completely reasonable length. Yeah. So I'm gonna name this 3D print experiment. That's just the truth. That's what it is. Export, and then the horn, not this one. Horn, shoulder horn. Export, STL. Now the one thing, this is by far the biggest print I've done since I got the printer. So I'm a little concerned that I'm gonna run out of filament. But oh my god, I always press upload when I have to add part. Okay. No. Oh, I see the issue. Okay. One part. Add one part at a time, I guess. Okay. 1, 2. And you know what's better than one horn? 2 horns. That's it. Yeah. We should flip these guys. Yep. That's it. Flip these guys. And you want to make sure in Bamboo that you enable support, because for some reason support is off usually. I mean, I totally understand. Support is terrible. It's ugly. But I don't remember where to enable support. Prepare, back to prepare. Range of objects. Okay. What does advanced even do? It doesn't seem very advanced. Preview. Total time only 2 hours. Slicing parameter. Did you know that you can view all objects on a table and change settings? Oh. No, I didn't know. Where? Here. Okay, objects, global settings. Okay, there we go. Support, enable support. Very important. Okay, slice the plate. Print time went up slightly. Some support here were on the shafts. We knew about the shafts, right? Some supports on the holes for the servos. Usually, I don't think we need supports for holes usually. So if you increase the threshold to 45, you shouldn't need support for, I guess. Oh, and last time I did tree support, that was really cool. Critical regions only. All right. Yeah. Oh, interesting. No support there. Okay. So this will be an interesting print. Let me see if I think the printer's up. Let me turn it on. If anyone played StarCraft, the torso shape reminds me of the battle cruiser cockpit shape, right? A little bit. It's kind of like hammer shape. Kind of looks like that. Printer should be on. Yep. Okay, cool. And so we're gonna print these, and I'm gonna go to sleep. I'm gonna trust that 1, we don't run out of filament. 2, the print doesn't fail. And then we'll pick up tomorrow. We'll assemble tomorrow, and we'll do the whole servo calibration. We'll do servo calibration, assembly. And we'll have, for the first time, 3 joints. So that should be cool. Anyways, thanks a lot for watching. I feel like I had fun. This feels like we did quite a lot today. So that's cool. This dog is actually starting to look like a real dog, which is awesome. And so I'll see you guys tomorrow.
One eternity later.
Hey guys, we're back. It's been a long day. We did a lot of things today, and I just got home, and I'm just looking at the prints for the first time. So this is what we printed last night, the torso as we call it, and a new servo horn. And we're in the kitchen, and when we're in the kitchen, that means we're gonna assemble things. So I'm going to over the next. I told myself if I do this in under 1 hour, I can order Chick-fil-A. So we're gonna assemble the leg onto the torso, just kind of like so, and it's gonna look like this, and we're gonna wire those servos, and we're gonna get the shoulder joint moving, and then we're gonna try to learn as much as possible from this torso to see if it's good. If it's good, we'll print the entire torso. If it's not good, we'll make changes, and along with the rest of the legs. And tomorrow, so today's Saturday night, tomorrow I hope to print the entire dog and assemble the entire thing. Now, right off the bat, I can already tell there's things that are not great about these. First of all, it's too heavy. It's very, like if you compare these with how the leg looks, you can tell like the same person didn't design it. This is so heavy. These walls are so heavy. There's so much plastic here. We can trim a lot of it. Second of all, just as you try to fit the servo here, this is where it fits. You can already see that the wire routing here is awful. It's like straight onto basically onto a wall. And you can already tell that one of the screws here on the servo, because it needs to go from the inside, it's gonna be impossible to reach. So I was actually planning to take a knife and just, like a kitchen knife, and just cut here across. I think since the infill is kind of low, I think that's gonna be completely possible. But yeah, I guess that's where we're gonna start. We're gonna try cutting that wall off. Let me see if it's even possible. I mean, of course it's possible. It's just, I should have said, let me see how bad I want it. Now, unfortunately, to connect this leg to the torso, we do need to remove these servos, and removing those servos means removing these screws, and that means when we put it back together, we need to initialize the servos again, which is I don't know, extra steps, kind of annoying. I always kind of forget how to do that. And okay, in theory, you can just take a knife and just go through there. It's not gonna be the smoothest thing ever. And you might want to wear some safety gear. Maybe a corrugated knife's not the best. And yeah, so the reason why I think removing this wall will help is because like if we have the servo here, we can reach the screw with an Allen key coming from here, except this wall's on the way. So we don't really need to remove the whole wall. We can just kind of like make a slot. Let me see if this knife is better. So it's like cutting onto, not quite butter. It's more like a, maybe like ice cream that has been on the freezer, sorry. For not super long, but like, for enough time to be hard. If that makes sense. Hopefully that makes sense. It would be easier if it was like butter, and maybe if we heat it up, it could be like butter. But I did mention it is Saturday night. It's been a long day. And it's kind of like, just want to do it as fast as possible. Of course, if you're doing this at home, you should wear safety gear. I'm a professional, so I can just cut things like that without safety gear. Because that's what professionals do. so you see I actually did cut through it, but it doesn't want to come off right away. Understandable. And remember the promise I made to myself, if we finish this within an hour, we can get Chick-fil-A. Else, we're having salad, because we're trying to get a six-pack. Alright. Alright. Okay. So weight reduction looks much lighter already. And so without that wall, I'm pretty confident that I'll be able to reach the inside with an Allen key. It won't be like a joy, but it's doable. Alright, so what should we do first? So let's put our knives away. And to think about it, so this guy goes here, like so. And then, well, it will go in when I put a screw in. This guy goes there, and then this guy goes here. And the screws for this guy come from the inside. So that should be screwed. So first we should screw this here. We should initialize these and screw these on neutral, like 90 degrees. Then screw these to here, and for that we need to remove the servos. And then reassemble these and then come back here. Alright, that's the plan. Sure, I've written it down somewhere. Alright, so first step is to initialize this guy. We're gonna do the old Arduino. I'm just gonna fly through the code because by this point we already have a public GitHub repo, and if you wanted to see the code, you can find it there. It's all very simple code. Honestly, I don't even write the code myself. It's ChatGPT's code. I have no shame in saying that. Yeah, it's ChatGPT code. So I just told ChatGPT, I have an Arduino Uno, I want to make one servo and set it to 90 degrees and hold it there. This servo has a range from 0 to 180 degrees. Speed up some code. When you're doing this, the code is super simple. Honestly, I didn't really need ChatGPT. But just make sure when you run the code to check which pins did ChatGPT assign to the servo. And it's kind of like, it's super duper easy to know, because it'll say, servo attach and a number. And for example, in my case here, it says servo attach 9, so that's pin 9, obviously. You knew that. And so now, if we do, I'm just setting the ground, setting voltage to 5B, and then digital pin 9, which is what ChatGPT just randomly decided. So this should be at 90 degrees now, and I chose 90 because these things go here, and the leg can kind of like move 90 degrees if this is neutral, and this servo has 180 range of motion. We can do 90 degrees this way and 90 degrees this way. We'll never go this way, but we could in theory. We'll never do it, but yeah. So I think that makes sense. Sorry, I thought I was talking to it. It was making noises. So now I'm gonna put these on. These do have 4 holes, so I'm gonna try to line up the 4 holes to the walls of the servo so it's parallel. And this might require some convincing from a hammer. It looks a little stiff. We do not have a hammer, but Now I never quite remember the right screw to use for these servos. It's an M3, and I appear to have misplaced my Allen keys. It's probably in here, and there's a bunch of Allen keys. I do not label my Allen keys. This is not the right one. Sometimes I get lucky and just pick the right one. I don't call it luck, of course, I call it destiny, but it is almost the same. Now, when we printed these parts last night, and you might remember better than me because it's in the same video. I think we used no support for this guy, and so this inside surface is a little rough. Just gonna try to clean it a little bit. Even though I told Arduino and ChatGPT to make sure that servo is holding position, I can hear some movements on the motor, which means like the potentiometer must be drifting. Anyways, it's important to make sure it's holding as you tighten it, because you're applying a torque in the pinion, on the servo pinion, and so it could continue shifting. So I'm afraid that's not long enough, I think. Kind of suspicious, but it could be because just the surface is not clean on the 3D printed part. Let's try a slightly longer one. What I have here is like a set of different M3, M4, M5 screws, different sizes, with washers, with nuts, which you can get from AliExpress or Amazon, I guess. It's the cheapest way I find of buying hardware. Home Depot is super overpriced. McMaster car is like expensive. So yeah. Okay, this isn't perfect 90. Yeah, I'm just gonna go for it. As you screw it, you should hear, if the servo is holding position, a high-pitched noise, and this is just the motor fighting the torque that you're applying, trying to hold position. This is to be expected. The one thing that I'm not entirely sure is how to tell when the screw is all the way in. I guess that's about it. Yeah, so that looks pretty good. The alignment is not perfect, I'll say that again. Maybe we tighten this a little bit. But it's pretty good. It's pretty good. Okay, so now that we have this, remember the next step is to unscrew these servos so we can screw these onto here, like that, like so. Like so, yeah. Yeah, it'll look like that. Which, by the way, I don't know why this has to be a separate part. I think this part could just be this part. I think we're gonna bond those parts together. We can remove one part right there. Now, I did think of what if we can do this without removing the servos? Wouldn't that be nice? It would be nice, you're right. It's just hard to reach in here with an Allen key. There's literally no space. So unfortunately, servos have to go. So let's do that quickly before I change my mind. This is of course the wrong Allen key. We can never get the right Allen key just by guessing. That's not allowed here. Okay, this is the proper one. Now these servo screws are screwed straight onto the plastic part. So there's a small chance that they won't go back in, but I like my chances. I like the odds here. Man, I hate wires. This is already assembled, so we don't really need the Arduino anymore. The other thing I have is this guy here, which should in theory make things much faster. That is, as long as we can actually make it fit, which is the problem. It's possible. It's possible. Would you say that's the same size? No, that's not the same size. So this electric screwdriver thing, I just got it from Amazon as well. Got it for a different project. It's been a lifesaver. Got it for the drone. Drones have a lot of little screws. Now I will say building that drone was more fun than flying it. Flying it is extremely hard, and I actually haven't flown much. I do need to try harder. So all of these bits are either too small or too big, which is interesting. Let's try this one here. They're not labeled or anything. We can just kind of just go by the vibes here. This is it. That's working. So much easier. Okay, that's off. These electric tools always make me feel like a dentist. I feel like these are the kind of sounds that dentist tools make when they're in your mouth. It's exactly the same. I swear, it's like being in the dentist. Alright, yeah. So that's 8 screws in there. You can see it's really kind of like in there. It's not you. I also can barely see it. So you're not missing out on anything. Plus it's screws, guys. Come on, you've seen screws. Alright, so now those should be off. Now just because the screws are off, it doesn't mean the servos are gonna come off. Actually the servos are kind of locked in place by these other screws on the other side. So we also have to undo those screws. That of course requires a different bit, because if everything required the same bit, it would be too easy and these videos would be too short. And the whole point is to make videos that are very, very, very long. Alright, one. Oh wow, that's long. Alright, and one more in here somewhere. Yeah, found it. Cool. I really wish we could play music in this channel. Okay, so all the screws are off now. And, what are they? It's like off, but not super off. Okay. So once they're off, you just gotta give a little pop, you know, massage it out of the, it is a tight fit. I kind of forget where things are supposed to go. Let me grab a Sharpie. It's kind of like, once they come off, it's kind of hard to visualize where things are supposed to go. Alright. Okay, well we actually don't have Sharpies, and we're also out of Diet Coke. But let's just remember, you know, roughly where things are supposed to go. We have a lot of patience. This design is losing points in serviceability. Basically, it's probably easier to 3D print a new one instead of like what? Hold on, let me do some thinking here. Big brains. It's probably easier to 3D print a new one instead of like disassemble parts. Just go ahead and 3D print a new one. Will be faster. Alright, so this is gonna go in here like that. We need to find some little screws. I don't know how little actually. Medium-sized screws. And we're using these very fancy countersunk or flatheads, depending on where you are, where you live in this world. You might call them something different. But basically, they are shaped like a cone, and so they go into a hole that's also shaped like a cone. And their profile is very short, so they sit flush, which, you know, I guess it's kind of cool. If you've never watched the Aviator movie, the movie based on the life of Howard Hughes, you should watch it. That guy loved these things. I mean, countersink stuff. Mostly rivets, but I think screws are like the same thing. Man, oh man. If it was slightly longer, it would make things a lot easier. Only slightly. Let's not get crazy here. Let me try my longer screws here. This is another screw. Putting in screws is like an absolute pain. And I'm only doing it for one leg right now. Imagine doing it for all the legs. It's basically more pain. Something that ideally could change in this design. Would be nice. I wouldn't mind. I'm trying to get the thread started here. It's a little trick, Jedi trick, to get the thread started. Much easier to do it with fingers. Once we have some threads, now we can bring in the well, first of all, there's no chance I can I fit, oh, maybe I can fit this thing here. We're replacing the attachment, the bit once again, because it's way more fun when you need different bits. Okay, that's decent. Okay, so one is in, and we need 4. Now, do we actually need 4? Well, that depends who you ask. But, whoa. Okay, I was able to push that into the hole without threading it. That's not good. So we need to tighten these holes. Make note of that. Remember, tomorrow when we're back in CAD, remember, Gonzalo said that you need to tighten these holes. Oh, all of them are too loose. Unfortunately, I don't think the joint will absolutely fail, but we gotta get it right, especially because getting it wrong means we're gonna have to come back in here and fix it, and you can see it's very painful to come back in here and fix it. Don't want to do that. Okay, so this is what it looks like. You know, makes sense. Now we put it back, the other 2 servos back inside. Now which one goes where? I don't think it matters. We're gonna initialize both of them anyways. And I think we can screw them on before we do any of that. So I'm gonna screw both servos back on. And remember, oh actually we don't have to change attachment this time. The screws, man. We're gonna do another Jedi trick. This time, this one's called going against gravity. Newton doesn't like this trick. Okay, one is in. Good job. Let's do one more. Do we really need 4 screws? Can we get away from 2 each? What would Elon do? I think Elon would be like, you should try 2 screws and see if it breaks. If it doesn't break, we know it works. But like I said, if we remove the screws, then this video will get too short. And I'm all about making videos that are many, many, many hours long. I think that's what people want. Make something people want. Very, very, very long videos. I wonder what Mr. Beast would say of this kind of content. How would he improve it? Alright, next servo, one more servo. maybe we should be labeling these servos so we remember which one those were. Like it's not a huge deal, but you know, it might make initializing it easier. And I was also thinking of some ways of initializing it without having to connect them to power, using some sort of fixture. I think it will be possible. Like connecting them to power is not a big deal when we are only doing one leg, but we do need to eventually do the entire dog. So all these little kinks will get old very, very fast. And our screwdriver might actually be out of battery. So it gets old for the screwdriver as well, not just for me. Screwdriver is giving up, so I'm coming in with the manual help. And one more screw on the servos, and then back to initializing. Now, I didn't want to admit this, but I actually don't remember how to initialize these. As in, well, okay, so let's think of this. Think step by step. Oh wait. Okay, yeah, it goes like this. So this is the hip and this is the knee. The knee starts at 180 and the hip starts at 0. Alright, so let's start. I'm gonna start with the hip because it's bigger. And we're gonna start it at 0. So we need to change the code a little bit. The only thing I don't remember is what is the hip supposed to look like at 0? I don't know. Let me take a quick look at CAD. I don't have my mouse on, so it's not gonna be great, but I guess something like that. The knee looks like that. 0. All right, yeah, we'll just go with that. I could look at CAD, but you know I don't have my mouse here, so on shape on trackpad is even worse than on shape without trackpad. So I'm writing to change that position of the servo. You literally change one variable on the function right, and then now it's at 0. And now we'll put it kind of like this, I think. Yeah, like that. I might want to spend some time thinking more on how to actually properly do these reliably, because we cannot be eyeing it out. Like we can eye it out fine for one leg just for testing purposes, but once we have 2 legs, 4 legs, we actually want legs to kind of like, well, too much, right? Too much, so the robot can stand flat. Okay, so that looks like that, and then I'm gonna do like, I'm trying to remember what's the swept range on this one, on the hip. So the hip can go all the way up to 85. So if this is 0, let's see what 85 looks like. And I push this code as I hold it on my hand. It should be somewhere in here. Let's see it. This might be a little hard. Oh, looks about right. Cool. All right. So on to the next servo. You know, we're doing this much faster than how long this used to take me. Just we're getting used to it. But like I said, we still need to improve our strategies on how to connect things. I don't want people eyeing out anything, right? Like eyeing out is not a thing. All right, so we're gonna initialize this servo at 180. Remember, it's because it's technically upside down. So at 180, we said 180. 180 should be somewhere like here. The leg is like fully stowed. All right. So we put this guy in. I need to charge this guy after. It's been 36 minutes if anyone's wondering. we're still in Chick-fil-A time. If we get this done, we can order Chick-fil-A. I normally walk to my Chick-fil-A, but my Chick-fil-A is under construction right now. They're expanding, and I can only order. So it's like terrible. Anyways, our leg is back in one piece. Now, for the first time, we're gonna assemble the shoulder joint. The way this fits in is basically first you put in inside this hole this pin we made on CAD, like that. Guys, I screwed this up. Wait. Oh no. Okay, wait. Okay, we're safe. Oh. I think I put it on the wrong spot. Should I cry? No crying, huh? Alright, we're gonna assemble these upside down like this, because I'm not taking things apart again. Let me see if upside down even works. I guess actually. Interesting. Okay. Oh my god. I thought I had it right. Alright, looks like I have to redo the entire assembly process. That's on me, so I'll stop talking and I'll just time lapse this. So you'll just watch me do this really quickly. All right, now, just ignore what just happened there. Now that we have the leg assembled in one piece, the way we fit this leg onto the torso is you basically line up this cylinder with this hole here, which we produced in CAD last night. And as you do that, actually a lot of cables here, but as you do that, cable management, another thing to improve. As you do that, the servo holes for these one also line up perfectly. So it's really an effortless assembly experience. Anyone could assemble these. Really good. Now there's a large gap between the servo flange and the wall. I can push it, and it cannot comply. I don't know why it's complying. Somewhere it's complying. Of course, that's less than ideal. So let me investigate what's going on here. The gap shouldn't be that big. No, I think this looks clean. This looks clean. So for now, we could just push it, just force it, basically. That's one way of doing things. doesn't always produce optimal results, but it always produces results. Okay, so now we just need to screw in this servo. It really is a big gap. Just need to find the right ones for these. Okay, another thing that we got wrong here is the size of the holes to mount the servos. I actually have the exact same hole size as the flange. Instead of a hole we can thread into. So we're gonna have to use nuts in this case for this to work. So a huge miss on my side, but I do have to have nuts here as well. So so we can, you know, just kind of like hack this together. Really what I want to get to a point is where it's moving, and so that's when we're gonna see if we missed another biggie somewhere. Nope, those are too big. Oh, what if I just use bigger? No, that won't work. Using nuts is fine, except I hate nuts. So it's not fine in that sense. And I hate them because, you know, you have to hold them in perfect position, things come loose and all this stuff. It's another part also, as cost, as mass. The screwdriver has stopped working, just gave up, went on vacations. And I think maybe 2 will do for this one. Just the 2. Just the 2 of us. Just the 2 of us. I'm gonna get copyrighted. Oh my gosh. See what I mean? Like, nuts are a pain. I have to hold it perfectly. Hold it perfectly. I'm gonna just go with 2 nuts. I think that's more than enough. There's already so many bad things that we need to improve here. I guess that's what happens when you rush, right? Would you say I looked rushed last night? Was I rushing? Like in the Whiplash movie? Were you rushing? But anyways, this is basically the torso assembled. So the leg, you know, you can do movements like that. Of course, like that. And now we can also do things like this. So we can pee on things. And I guess we could do these. I don't know why we want to do that. And you can also fold it like that. We can do yoga. So maybe like the travel, you know, travel package, something like that. Or like that, you know. Very modular, very, very nice. So I accomplished this in 54 minutes, I think. And so as a treat, I'm gonna order Chick-fil-A. And while we wait for the food to arrive, we're gonna power these and we're gonna see just how it moves, you know, and stuff like that. And then maybe we put some thought in wire management, but after that, I'm probably gonna call it a night. We'll make a list of things I need to improve, but you know, I think it's looking better, you know, it's looking good. Yeah, just some big misses in terms of, you know, holes not lining up, assembly being hard. Yeah, always room for improvement, but I think it looks pretty good. What do you guys think? Comment below.
A few moments later.
All right, guys, I'm back. So I did get Chick-fil-A, and like I said, I had to order it because my Chick-fil-A was closed. And I gotta say, I do feel like a sucker. My order was $20. I ended up paying like 36 after fees, delivery fees, processing fees, all kinds of fees. Who are the people who pay these fees on the regular? Like, I just do not understand. And as long as people are paying those fees, don't tell me we're in a recession. Just do not believe you. There's people willing to pay that much for it's the convenience. There's something in this world I do not understand. Anyways, we're gonna get the shoulder joint moving for the first time. So here's the leg. Actually looks pretty cool from the top. The other thing that I've been thinking was that this gap here is actually unnecessarily too wide. There's plenty of clearance even here. There's plenty of clearance. I can fit my pinky finger. We can make these narrower. It will help with, just make the package tighter, and we'll gain some space here, some packaging room. We can fit something in there, like maybe like a Chick-fil-A sauce, for example. And the other thing I was thinking is like this torso, I have a lot of radiuses, a lot of fillets here. And the leg basically has nothing. It has sharp angles, it has chamfers, and that's why it feels like it was designed by someone else. So maybe we'll clean it up and just be more consistent. But with that out of the way, let me just clamp this down. Wire management is another thing to think about, just because, right now I have the wires going in here. But they should probably be routed through like the torso somewhere. If you were cycling like this, which will never happen, your wires are going to see a lot of strain. And then the other thing is, today I can probably make 2 servos move. I don't know if we can push the Arduino to move 3 servos at a time, but anything past that, I think we're not going to have enough current for the same issue we've discussed before. And it's like the Arduino can only output 800 milliamps for a period of time, and then it'll overheat, and then you cannot basically it'll just trip. So I do need to figure out a solution for the electrical stuff, and tomorrow I'm going to talk to a friend who's an electrical engineer. I might do a video call and include it in this video, so we all learn together. But I think he'll have some good solutions. And yeah, the Arduino power restriction of 800 milliamps is true even if you power it with an external source. It's not about that, it's more about, there's basically kind of like a fuse on the Arduino. It's a pretty thin board. It'll eventually get hot if it's putting out much current, and it'll melt, so they have some sort of fail-safe there. Put some sauce in there. Alright, so what I'm thinking, first we just cycle this joint here just for fun, and then maybe just to get a cool video we cycle maybe 2 at the same time, so the shoulder and maybe like the hip at the same time, something like that. It won't be as smooth probably. But okay, let's get started. Let's do one at a time here. I do have an issue here with my computer. Not having enough ports to support both the Arduino and the my mouse, so I have to pick one. Now the code I'm going to use, it's already on GitHub. I want to just modify what I have on the repo right now, and maybe I'll update it with new code, whatever comes out of tonight. Yeah, and then tomorrow should be a big day. We'll figure out electronics. We'll also go surfing, and we'll also fix the CAD for everything, and I want to just get started printing the entire body. Also, we had this to-do list from last night. We crossed out the shoulder joint is done, the torso is kind of done. We still need to figure out how to pack a Jetson Nano developer kit here. but I also want to add, changes to the body. So I'm gonna add here on the to do change. The servo mount holes are oversized. Change. The walls are too thick. So this part overall is just too heavy. There's too much material. Takes too long to print. It takes like 2 hours just for half the torso. What else did we say? Change. Oh yeah, we can remove the servo horn, pretty sure, and just bake it into the part that houses the two servos for the hip and the knee. What else did we say? Well, we say that the clearance was too much, right? So reduce clearance of the shoulder joint. What else did we say? I feel like there was more. There was definitely something going on axially on the shoulder joint, where it's like we had to really really clamp down the servo for it to fit. It was like a little longer than a CAD. So I'm gonna write check shoulder joint axial dimension stack. And we can add wire routing maybe. That would be nice. And I think I think that might be everything we've learned. Obviously, we're not gonna have a wall here, so I mean that goes without saying. I think we knew that was gonna be an issue from the start. All right, so those are our notes for tomorrow, and I'm gonna ask ChatGPT here to edit our existing code to add a new angle. And so if this is 90 degrees for shoulder, we could probably go up to here. I actually don't know if this is 180 or 0. But we can go full 90 here, and then on this side we can also go to full 90. So let's cycle it like that. So I'm gonna say, I'm gonna tell ChatGPT edit the existing code to add a third servo in the pin 11. This servo should cycle from 0 to 180, where neutral is 90 degrees. This servo doesn't care about the position of any of the other servos. Alright, so I'm just gonna give the code. I'm gonna let ChatGPT do the existing, do the full coding. Let's see what it comes up with. It's probably something that we can work with. I'm sure it'll be fine. And I also told it we're using pin 11. So for the first time, I'm telling it what pin to use. I'm gonna move things here because like my computer, it's just, again, I need more USBs. That's one reason to why I have a MacBook Pro, I guess. All right, so ChatGPT spilled out some code. This is all very simple Arduino code. There was some weird noise there. So it's just a continuous loop. It added a new servo on pin 11, like we said, and it's cycling in 5-degree increments. So 5-degree increments, it means it's gonna be a little jerky. Of course, the code is in degrees because we're using a servo library in Arduino. But actually, what that servo library is going to do is just translate that to PWM, pulse width modulation, which is basically microseconds, like values in the thousands. So 5 degrees is actually quite a few jumps in PWM. So it is going to be a bit jerky, but it's going to work. So I'm going to upload the code here, and we failed to upload. Classic. Uploading again. Alright, so now that when I connect it, it will cycle through full range of motion on the shoulder. Or explode, one or the other. Yeah, so very jerky, very, very jerky. but kind of cool, right? All right, let me stop it for now. I want to figure out what's 180 and what's 90. So yeah, that jerkiness is very easy to fix. Just take smaller increments, take smaller increment jumps. Not a problem whatsoever. Where it gets more complicated, and it's a new frontier for me, is like coordinating 3 servo movements at a time and building a controller. That's going to be entirely new for me. So this is 180. All right, so now we know that for this servo, 180 is up here. Interesting. Okay. I wonder if there's a way to power 3. Okay, maybe I'm not even going to try to power 3. The 3 servos. Okay, so let's cycle it. Let's cycle it in a smooth and nice way. I have the following code. I want to cycle the servo from 0 to 180 degrees in the smallest increment possible. Maybe 0.3. So let's see what happens if we take very, very, very small increments. Let's see how smooth we can make this happen. And the code is calling for 0.01 degrees steps. And if that doesn't work, we can try something else. Like, you're just using PWM instead of angles. Okay, cool. So I think we just tripped there because we hit it and, I don't know, caused a current spike or something. Or maybe not. The way I tell is I just touch the board, and if it's hot, I just assume something went terribly wrong. But it should be looping. The code should be calling for it to loop. Okay, so I see what's happening. It's taking small steps, but very, very slowly, and it's taking forever. I'm gonna remove some delays on the code, see if that speeds it up. I don't know why it's taking so long. Yeah. That looks good, right? I wonder how many times you can run these before something breaks. I mean, everything is smooth, but... And I do wish I had a power source so we can see how much current we're pulling right now. I'm gonna try to run 2 servos at the same time. Also, our envelope kinematics got, I think, more complicated now because there's certain positions of this leg that there's new possibilities to fall into positions where things are clashing, which is always fun. Yeah, but let's see. So I'm trying to combine movement for all 3 servos to see if that happens. So in this next scenario, we're gonna cycle. We're gonna keep doing this on the shoulder, and then we're gonna cycle the hip through its full range of motion, and let's see what happens. Again, I think we're pushing it in terms of just in terms of current and power available. In fact, I'm gonna stop this just so the board doesn't get too hot. But I think it's looking good, looking smooth. You know, I like that. So let's see. So I'm just gonna quickly read the code here. See, okay, so you added back delays. I'm always removing delays. Don't want delays. No need for delay. No need for delay. No need for delay. All right, move the bunch of delays here. It wants the hip servo on pin number 10. So this one's gonna be pin number 10. And let's hook up this hip servo, which would be this guy here. So it'll be here, and it'll be here. All right, and so I think if I'm just gonna go ahead and upload this code and see what happens. And so we're gonna connect one servo at a time here, just be civilized, see what happens on the shoulder. Okay. I'm not sure. I guess it is moving very, very, very slowly. So maybe I missed a delay or something. It is moving. Yeah, right. It is absolutely moving. It's just very slow. And we're on the right pin. Yeah. So I just re-uploaded. That's why it initialized the position again. I'm not entirely sure why it's going so slow. So it should still be 0.01. Alright, that's okay. Just for now, I'm going to increase it to 0.1 degrees, so it's going to move faster. Let's see if it's jerky. Alright, let's try 1 degree. And we're going to start at 90 degrees from now on. Okay. Alright, connecting one more servo. The leg servo, the hip servo, sorry. Should already test it out. I see. So for every loop that the hip does, for every loop that the shoulder does, the hip is like moving. A little bit, which is fine. It's just too slow. So let me speed things up here. Oh. So let's not go all the way to 0. I'm going to reduce the range of motion here a little bit just to speed things up without having to rewrite the loop. Alright, so it's going to start minus 45 is the minimum. Yeah. Alright, let's see where servo 2 is at. Servo 2, servo 2. Servo 2. asking ChatGPT that I'm telling ChatGPT that I don't want to wait for Servo 3 to finish its loop for Servo 2 to start moving. So I'm asking it for them to move at the same time. Let's see what it generates. The code is getting very messy. A lot of for loops, which we'll eventually have to clean up. I just want to see it move. And the shakiness, obviously, it's like this isn't under the exact load scenario. My clamp here isn't. It's probably not helping. So I'm not worried about the shakiness. The whole system is vibrating, but I'm not worried. Are you worried? You shouldn't be worried. I'm also not worried here. It's just like it doesn't look cool, you know. This screw is coming loose. Servo 2 is too jerky. I need smaller 1-degree steps. I know. So okay, well this is completely my bad. It's bad code. But see the shoulder's not that bad. And yeah, some of the screws coming loose. I think that's something that we predicted on the first video we ever made. Like we knew that these would come off, and we talked about replacing them with nylox, and just never did, because it was never an issue. But now we're getting to, now that we're moving, that's when things start to like shake off, basically. There's that Taylor Swift song. That's, you know, it's very real. Shake it off. Robots do shake off things all the time. You gotta beware. Alright, motion should be a little smoother on the hip. Okay. Alright. I like that. Ooh, look at that. Lucky clearance. Alright, guys. Okay. I mean, it looks cool. We're all thinking the same thing, right? Can it go faster? And yes, it can. How do we make it faster? I do want to make things a little faster. Let's see what ChatGPT suggests. Reduce delay times. Actually, I don't think we have delays, so ChatGPT, you're wrong. Oh, there is a delay. Increase step size. That's absolutely not the case. All right, I've eliminated the last delay. Yeah, that did not help at all. I guess our steps might be too small. Let's see if we have a step variable. We didn't know. We might. Servo 2. Right angle. Let's do that. Let's do the serial monitor is. Turn off auto scroll here. Okay. Well, I don't think we need faster for now, right? Like this proves that, you know, the kinematics, like we didn't miss anything. Things are not clashing. And let's just go back to this smooth only shoulder motion, just to remind ourselves of what that looks like. just wants to tap the cable. I do wonder, how can we make this even faster? Let me see. How can I make this even faster? Let me see how fast we can go. So GPT's best idea for making things go faster is increasing the step size. I'm gonna increase the step size by 2 magnitudes. I don't think that's gonna do it, but let's try it. Let's say we're gonna type this somewhere. I used the brackets backwards. I'll do this. Don't hurt me. Oh. Is that faster? See, when that happens, I just assume that it's because the board has flipped, and it also disappears from my serial monitor, so I just assume it's because, you know, the board has, we've tripped the board. Oh, dude, no. Bullshit. Yeah, an easy way, just don't get stuck in an endless loop, just disconnect power for your servos. When you restore power to your Arduino, so it doesn't trip again. But anyways, I think I'm gonna call it for tonight. We have a ton of stuff planned for tomorrow. We'll see how far along we get. Again, the plan for this weekend was to build the entire robot, at least have the structures printed and assembled. And I'm still very motivated to like crush that goal. So I'll see you tomorrow.
Day 3.
Hey guys, so I didn't get any time to work on this project on Sunday, but I didn't want to leave the video hanging. So I'm just gonna wrap it up here. Let's quickly look at everything we did this weekend. So it's right here. So basically at the start of this weekend, we only had a leg and it was moving. We basically built this shoulder joint. We got it to move. We have a first pass of what a torso design looks like, and it's printed. And we also have a list of lessons of things that need to be fixed. So next time we work on these, hopefully during the week, we basically can just focus on fixing the issues that we have identified. And I've also been thinking a little bit more on how to power the servos and what kind of electronics we need for that. So we'll probably need a buck converter, some bus bars, and we'll just make do with the Arduino as a microcontroller for now. And so I'll talk about that more in the next video. But the goal for the next video will be to have the fully assembled robot in one piece. So I thought I would leave it on that cliffhanger and make this video a little shorter. I'll try to make videos a little shorter in general. Next video, full dog for the first time. You'll see. All right, have a good night.